So let's stop this. All right, the first thing I would like to do is I would like to get on into talking about what's going on for the rest of this unit. I always kind of like to start off the Mondays talking about what's kind of going to happen there so everybody knows what's happening and when things are going to be due and all that kind of good stuff. We'll make this big then. All right, so we are currently at the 26th today. So we're going to do thermochem notes number 3. We're talking about the heat equation. It is mathy. The math is going to start. Thermochem has a lot of math in it. So that's going to start today. Then tomorrow we're going to talk about metals in water. On Wednesday, we're going to practice Q calculations. Thursday, we're going to do the lab that those of you at home did last week. We're going to do that on Thursday. And then Friday, we're going to have a quiz, Q is equal to MC delta T, which we're going to learn today. Okay. Then if you care, next week when you guys are off, we have, we're going to do a different lab. It's called the Bolt Lab. That is some very seriously hard calculations. So I suggest you're there because that quiz is going to be a doozy. We do not have school on the 3rd. We're going to practice the Bolt metals, and then we'll do a lab, and then you'll have your quiz there. And then the last week of the unit is week 12, which starts on the 9th. We'll talk about states of matter, do some review, and we will have our tests. The next big test in this class is on the 13th. So if you're of the planning type like myself, this is how the rest of the unit is going to shake out. And everything is in that packet. So you want to keep that packet the entire time. Okay, perfect. So that's what we're looking at here. Let's get into our notes. So thermochemistry, last week, we just talked about on a conceptual level. We said thermal energy is energy transferred. If I touch an ice cube, I feel the energy being removed from myself. If you put your hand in boiling water, that would hurt because it would apply a lot of energy to you, that type of thing. We also talked about entropy. And in order to be spontaneous, you have to have an increase in entropy. You have to be exothermic, all that kind of good stuff. So I'm sorry that you guys weren't here for that because some of that stuff was rather challenging. But that was in the last quiz. And the lab on Thursday, we'll practice all of that again. So now what we're going to do is we're going to start to quantify all that. We're going to put some numbers to that information. And the first thing that you have to know is that there is this thing called specific heat capacity. So let's define it and then talk about it. Specific heat capacity is the amount of energy needed to increase the temperature of 1 gram of a substance by 1 degree Celsius. The amount of energy needed to increase the temperature of 1 gram of a substance by 1 degree Celsius. So what you can think of is you can think of it as like a cost in how much it takes to heat something up. So it's also, that's a very technical definition. The easier way is you can think about it's how hard or how easy it is to heat or cool something. So do you have to heat it for a long time in order for it to heat up, or does it heat up fairly quickly? So my example would be like if I had some water and you want to make some mac and cheese or something, and you get a bunch of water and you put it on the stove and you turn the stove on, and then you have to do what? You have to wait and wait and wait. Because does water heat up very quickly? No, it takes forever, right? But if I were to take a metal pan, like baking pan, and put that on the stove, turn it on, that sucker's going to get hot. Or if you have like a pan that you're using, so they get very hot very quickly. So metals heat up quickly, water does not. Partly you would say it's because it's an insulator or a conductor, but this thing called specific heat capacity is just like melting point, density. It's a physical characteristic of matter that says how hard or easy it is to heat it up. The unit for this is challenging, okay? It's joules per gram degree Celsius. Joules per gram degree Celsius. And you can remember that because the definition is in this unit. This helps you remember, okay? So basically what the unit is telling you is joules is energy. Remember, joules we talked about last week is thermal energy per mass times temperature. So it's how much energy it takes to heat 1 gram, 1 degree Celsius. So if you can't remember the definition, if you can remember the unit, then you know what specific heat capacity. And again, you can think of it as a cost. Does it take a lot of cost to heat it up? Or does it take a little bit of cost to heat it up? And if it takes a lot of cost to heat up, it also takes a lot of cost to cool down. So we kind of already talked about it, but my question here is if you want some delicious mac and cheese, you're like, but I want it now, you're stuck waiting for the water to boil. Okay. And the reason why it takes forever for the water to boil is that it takes so much energy to heat water. Water has a high specific heat capacity. Okay. Awesome. So the specific heat capacity of water, I'm going to give it to you now. It's one thing you have to memorize, just like you know the density of water is 1, and you know that it boils at 100, and it freezes at 0, all that kind of good stuff. The specific heat capacity of water is 4.18 joules per gram degree Celsius. I know it doesn't seem like a number that means a lot to you, but as we start talking about metals next week, as we start talking about different things, you'll see that specific heat capacities are rather low. Okay. So you need about 4 joules, and that's how much it takes to light a light bulb up for about a minute, okay, to heat up just 1 gram, 1 degree Celsius. So if you want to heat up a whole bunch of water for your mac and cheese, it takes a lot of energy to do so. Okay. If you ever are taking a standardized test, a lot of times the other thing they're going to talk about the specific heat capacity of water is they're going to talk about weather and climate. And why is it so lovely to live near the water? One of the main reasons why, okay, is because of this high specific heat capacity of water. On a warm day in March, okay, so it has been, your pool has been frozen all January, all February. It starts to kind of get nicer in March. Would you want to jump into a pool in the middle of March? No. Has the pool warmed up by March? No, the air might be warm. Okay, but the water in the pool takes forever. Okay, the water is still cold because in a pool, it takes a ton of energy. So the sun can warm up the air, but it has a hard time warming up the water. And I gave you a little kind of breakdown of some of the most common specific heat capacity. Dry air has a very low specific heat capacity. It is easy to heat it up. Water, okay, is extremely hard to heat up because it has a high specific heat capacity. So that's why even if the air is warm, but it's also the opposite. Does anybody have a pool that they go to in the summers or anything like that? In the night, if it cools down in the air, you can still jump into the water and it's still fairly warm because it retains that heat. Okay. So then the other reason why the weather is so nice on the coasts is because, okay, the amount of energy you need to heat and cool that water is tremendous. So it keeps your climates really nice. Okay. And you can paraphrase that if you would like, but it is hard to heat and cool water. And it's easy, okay, to heat the land and the air. This is because it has a low specific heat capacity and water has a high specific heat capacity. It's how much energy it takes to heat it up. Okay, and we are going to practice specific heat capacity a whole lot more. So if you're like, I don't quite get it yet, that's okay. We're going to get there. This is your first intro to it. Okay, awesome. So that is one of the more challenging ideas for this whole week. And hopefully we can drive it home with our lab tomorrow. Wonderful. All right. Let's get into some math, shall we? You guys are like, I'm ready for the math. Let's do it. On the back, we're going to talk about what's called the heat equation or the thermal energy equation Wonderful. I can guarantee you if you go to college and you have to take any intro to chem, you're going to be doing this equation and you're going to be like, this stuff is easy because I learned it in high school. You got it. All right, so the heat equation is as follows. Q is equal to Q, and we'll talk about each of these variables, is equal to M times C times delta T. And we threw the word, the triangle, this triangle here is delta. Okay. Q is equal to MC delta T. Oh, when you're super cool, okay, you can call it Q is equal to MCAT. So if I say, oh, that's an MCAT problem, and you're like, what kind of cat? I don't really know. I don't know. So I don't know why. I mean, obviously they kind of made it like this looks like an MCAT, or, you know, I don't know, maybe you see like a kitty cat here. No? Okay. All right. Or you can just say that the delta looks like an A. So Q is equal to MC delta T. Let's go through and talk about what each one of these variables means, and then we'll figure out how to plug it in. And then once we can do that for the rest of the week, we can have a little more fun playing around with the idea of specific heat capacity. Q is the quantity of thermal energy, also known as heat. So if you see the word heat or energy, you know you're talking about Q. Quantity of heat or thermal energy. The unit for Q is joules, or you can just write a capital J. Joules, capital J. M is what it's always been. It's still going to be mass. Like if you think about our density equation, D equals M over V. Anybody remember the unit for mass? Grams. Wonderful. Or just a little g. C is the new thing that we just learned. C is specific heat capacity. Specific heat capacity. You might hear professors call it specific heat, heat capacity, specific capacity, but I like to use the big term so you know all of it. We just said on the other side, the unit for that is joules per gram degree Celsius. And then delta T, we said that this is a Greek term. Little triangle means change in temperature, change in temperature. And you're always going to keep it positive. Even if you subtract and you get a negative number, just take the absolute value and you always keep it positive. Does anybody know what temperature unit we're going to use in this class? Not Fahrenheit, but you got it. Celsius. Very good. Okay. So again, here, in order to find the change in temperature, you always subtract temperatures because change means different or subtract. Okay. So I'm going to do a couple of practice problems with you, and then I'm going to give you some time in class to do some practice problems on your own. So I have 3 that we're going to do together, and then there's a worksheet that you guys can do. And once we can do the math, then we can add the labs in, and we can do different things, demonstrations, and we can get all mathy on that, okay? So the first most important thing is that you read the equation. Okay, I know people love math problems that are reading, but we're here. Another thing that I do, I put this on the side just to get you started. If you want to pull out your variables like that, you're more than welcome to. I eventually make it go away because you don't have to. But sometimes if you can kind of say, hey, I know what these variables are, it makes it a little bit easier. So it says, an oven transfers 66,195 joules of energy to an aluminum baking sheet. Okay, so this is joules. So which one of the variables is this one going to be? That's going to be Q, MC, or delta T? Q, very good. The baking sheet has a mass of 425 grams. Well, that's easy. That just tells me the mass here. How many degrees did the temperature of the baking sheet change? So my Delta T is my question mark. And it tells you, you'll either see the specific heat capacity given to you. You might see it in a data table. I think maybe on the next page. Okay. If you take a look on the next page, it's in a data table. You can always look there. Okay. But it says the specific heat capacity is 0.89 joules per gram degree Celsius. Now, all we have to do is put in our variables and solve for the missing one. So Q is equal to MC delta T. That is my equation. My Q is 66,195 is equal to, my mass is 425. My C is 0.89. And you can either write delta T, or if you're like, I like X, then you can turn it into X, whatever you want. That is what we are trying to find. All right, so what's the first thing I'm going to do in order to solve for X? Got to multiply the 425 times 0.89. So I'm going to multiply 425 in my calculator by 0.89, and I get 378.25. And this side is the same. Does anybody know now algebraically what I do in order to get X or delta T by itself? You've got perfect. We're going to divide both sides by 378.25. Boom. Once I divide that by itself, it gets on its own. So in your calculator, you would put 66195 divided by 378.25. And I know you can do that, so I'll give you a chance to do that in a second. But you get 175. Let's take a moment very quickly. I know you want to talk about sig figs. No, you don't. Let's talk about sig figs, though. Does anybody like dying to still do significant figures? You're like, please, I'd like to. No, nobody wants to do them anymore. So let's make an understanding right now. If we agree that we're all going to go 2 numbers after the decimal from here on out, always round, 2 numbers. So I'm talking about even if you're like 0.0025, okay, you still have to have 2 numbers, not 2 places. If we all agree to only round 2 numbers after the decimal, I will never do sig figs again. Can we agree on that? Beautiful. Okay. So 175 is fine. And it says, I want to know the temperature. So what is the unit for my 175? You got it. Okay. So the answer to that question, if I have a baking sheet that's 225 grams and the oven gives it 66,195 joules, what's the temperature going to change? It's changing to 175 degrees. Okay, perfect. I'm going to do 2 more with you, and then I'm turning you out on your own to do it all by yourself. What is the specific heat capacity of a substance? So what am I trying to find? Q, M, C, or delta T? Trying to find C. Thank you. That absorbs 2,500 joules of heat. That is Q. When a sample of 100 grams, that's M, increases in temperature from 10 to 70. Oh, hold on. I see that it goes from 10 to 70. What is my delta T? How much did it change going from 10 to 70? Difference between 10 and 70 is 60. Okay, you just subtract. So it went from 10 degrees to 70 degrees. You subtracted, that means it moved 60 degrees. All right, plug it in. Q is equal to MC delta T. Q, 2,500. M, 100. I'm looking for C, so I like to just leave C there as a C. It's up to you. And delta T is 60. Does anybody have any questions on how I got the numbers, where I got the numbers? Is that hopefully we're all good? Then algebraically, this is already by itself, so I'm going to add just leave that alone. 100 times 60 is 6,000. And I'm going to leave my C there. And again, to solve for C, I just divide both sides by, remember, you always have to take the 1 and get it by itself. So if C is over here, that means I'm taking the 6,000 and putting it there. When I do 2500, I see some people calculating. Beautiful. 2500 divided by 6000. What number do you get? The tiny one. Again, 2 significant places after the decimal. I won't call sig figs. But does anybody remember the unit for C? Joules per gram degree Celsius. Yes. Feeling good. All right, I'll do one more with you when we locate something else. Then I'm going to leave you to do your lecture questions and the next worksheet because it's easy when I'm doing it. Maybe I'll stop halfway through and see how you're doing it here. How much thermal energy is released to your body when a cup of hot tea containing 200 grams of water, so 200 grams, my math, is cooled from your body temperature to 37 degrees Celsius? Man, you are just like this, giving me nothing. So the first part of the question is, it says how much thermal energy. So I'm trying to find for Q. And you're like, I don't see a C, but you know that it is hot water. Can you look on your other page, on the other side of your paper and find the C for water? And then what are you going to do to figure out your delta T if you're going from 65 to 37? I want you guys to figure out the rest of these and then plug it in, and I want to see you solve for it. I think everybody can do this from here. I got you right to the end. I'm going to walk around. Those of you at home, finish this, and then we're going to go over it. Let's see you do this. Let's see if you can finish this off. You just need to find the C and the delta T, and then plug them in and solve. What's that C value for water? Yeah, there we go. Also, it's real big. Right. You got it. What are you doing here, Mr. Naratoxin? Oh. One is energy to be 1 gram. just 1 gram of water, 1 degree. How did I? 4.18 is how much it takes to heat up 1 gram, 1 degree Celsius. Yeah, it's 4.18. Yep. So 1 degree Celsius is 4.18 joules. 4.18. It's the same number up in the box up here. Okay. You got it. Very good. I must it. You didn't get either. 1 degree, 4.18. Yeah. Yeah. That's going to give you your delta. Awesome. This is the beginning temperature. That's the ending temperature. So all you're going to do is subtract. You got it. Very good. Very good. Very good. Yep. So it's 28. Yeah.
Now, the other thing is, we're talking about water, right?
You don't have to because you already are in here. I see exactly what you're saying. I love it. It's already in there. It's built in the equation. Perfect reason. Right?
You don't actually front page in the notes.
Yep. We'll tell you your specific capacity of water. Nice. Oh, I see some people doing some great stuff. I love it. I love it. Math is so fun sometimes. All right, so I want to know Q. That's what I want to know. I know I have 200 grams. I looked on the other side, and I know it's water, so it's 4.1 is my C. And then when I take 65 and 37 and take the difference, I get 28 degrees. And in order, all you have to do to solve for Q is multiply the 3 together. Hopefully you got a nice big number. 23,408. The unit for Q is J, joules. You got it. Okay, so this is just getting, I know this is unfun, but tomorrow we'll kind of attach a lab to it. But what I want you to do right now, we have about 15 minutes, so it's plenty of time, plenty of time. I want for you guys to turn to the next page, okay? Q is equal to MC delta T. I want you to see if you can remember the definition and the units, and then I want you to go through and try some of these practice problems. I also want you to open up your Chromebooks, and I want you to answer the 3 lecture questions. If you can fill this thing in, this might help you with your 3 lecture questions. That might be more than half of it. And then remember, if you're looking for a C value, you might want to write C right here. If you're looking for a C value, because you don't see it, okay, like here's water again, boop, you can always look up in this table for your C values. So I'm just going to walk around. I'm going to see how everybody at home is doing. Just putting in some math work here today. Q is equal to MC delta T, and fill in for the missing variable, okay? And get those 3 lecture questions going. So you got plenty of time to do both today. Let's do it. Three lecture questions and